In this example, we're going to do something a little different than in the previous examples, in that the transmission lines connected to a two-port device that we're trying to analyze to determine the scattering matrix, those transmission lines connected to it are not only different than this transmission line in the middle, but they are different from each other. So at port 1, we have a transmission line with a characteristic impedance of 25 ohms, and at port 2, one with a 100 ohm characteristic impedance. Inside of the two-port device is a length of transmission line, a lambda over 4 quarter wave length transmission line. It has a characteristic impedance of 150, which of course is different than either the 25 or the 100. And so this looks like maybe a bit of a contrived circuit that we're trying to analyze for scattering parameters, but this is a kind of a structure that we frequently see in microwave circuits, useful ones, things like multi-section matching transformers, for example. So I want to show this to demonstrate this with an example to show how we would approach a circuit of this type. And again, the unique thing here is that this transmission line characteristic impedance of 25 ohms is different than the characteristic impedance of the other transmission line on port 2. Now, you probably hope we recall, that we analyzed and determined the scattering matrix of a length of a transmission line in an earlier example. And you might look at this and say, oh gosh, if I look at the inside the two ports inside the device, it's just a length of transmission line. And can't we use that same result previously to analyze this structure? Previously, this was the scattering matrix that we determined for a arbitrary length of transmission line. But in that case, we have a situation where the characteristic impedance of the transmission lines connected to each port of that two-port device were identical to the characteristic impedance of that transmission line inside itself. Z0 connected in one side, Z0 connected on the other, and then Z0 likewise forming the two-port device a length of transmission line. So we just really had a continuum along that structure. There was no discontinuity, no change in the characteristic impedance as we moved along the structure, and it led to this scattering matrix. In this case, of course, the transmission line characteristic impedance attached to either end are different from each other, likewise different from the characteristic impedance of the transmission line in the middle, and so this result that we previously obtained has no value here. It was a different circuit since the transmission lines connected to each port were different. This structure then, where we have 150 ohm characteristic impedance, 150 ohm characteristic impedance, and once again 150 ohm characteristic impedance with a length of transmission line. If this were our circuit, then we could use the previous result. This would be our scattering matrix for length of transmission line. Of course, if it's quarter wave length, then this beta L becomes, or e to the minus j beta L would simply become a minus j, e to the minus j pi over 2. In that case. But of course, this is not the circuit we have and we're trying to analyze here. Instead, this is our circuit, of course. We have a 25 ohm characteristic impedance here and a 100 ohm characteristic impedance here. So how do we find the scattering matrix? And of course, there's lots of ways of going through and analyzing this microwave circuit. We have lots of tools in our toolbox to do that. Boundary conditions, we know the telegrapher's equation, the solution for each of these three transmission lines, and we could apply boundary conditions, solve for the different wave amplitudes, plus and minus, and from that determine the exiting or scattering wave on each of the two ports in terms of an incident wave on each of the two ports. But the method we're going to use here is to apply our match source and our match load. So to get an incident wave, let's say on port 1, we're going to put a matched source over here. And that match source will generate an incident wave, and it's a special case since its characteristic impedance will be equal to 25 ohms. And we can even replace the structure with its equivalent circuit. The transmission line of 25 ohms will transform a match source into another match source. Likewise, on this side, we're going to terminate this in a match load. By match load, I mean 100 ohms. So there's no reflected wave here on this transmission line. And in that case, the input impedance is going to be 100 ohms. And so we're going to replace the entire structure with its equivalent circuit, a 100 ohm resistor on this side. So we have a match source with a source impedance of 25 ohms here, a match load with a load impedance of 100 ohms here. And that's how we are going to attempt to determine the scattering matrix for this structure. So here's our resulting circuit now that we are going to analyze so we can find the scattering parameters. Ultimately, we're going to try to find the port impedance, the port voltage V1 and the second port voltage V2. Since we've replaced the transmission line with equivalent circuit on either side, we can't really go through and analyze plus or minus waves propagating on these structures. All we can do is determine the total voltage at the two ports. But once we know the total voltage, we can determine the incident scattered waves easily because we have a matched source on one side and a matched load on the other. Which brings me to a very important point, a mistake that students frequently make in this case. They think, oh, I'm trying to connect a matched source to the structure. I should make the source impedance 150 ohms, the Z0 here, or I'm trying to connect a matched load over here. I need to make a resistor which has a value of 150 ohms. Well, that's incorrect. The matched load is matched to the transmission line characteristic impedance attached to port 2, and that was 100 ohms. And the matched source is source impedance that's matched to the transmission line characteristic impedance connected to port 1, and that impedance was 25 ohms for that transmission line. And so when you have a structure like this, neither the source nor the load impedance will be equal to the characteristic impedance of this transmission line, because this transmission line characteristic impedance was not the characteristic impedance of the port 1 transmission line nor the port 2 transmission line. So be very careful there. Make sure you don't make that mistake. Once we look at the structure, it's a structure we've seen before. We have a source, we have a load that terminates a transmission line. To a certain extent, there aren't many special cases here with respect to this circuit. This load of 100 ohms is not matched to the transmission line characteristic impedance of 150, nor is this source matched to the characteristic impedance of this transmission line. So this is a very sort of general circuit. We have to treat it in this way. The only real special case we have associated with this is the fact that the line length is lambda over 4. And because it's lambda over 4, there's a few tricks in our toolbox that we can use to analyze the circuit that will make things much simpler. I suggest that what we do is apply the accordion. In other words, we come up with equivalent circuits. Because we have a quarter wavelength transmission line, we can immediately determine the input impedance of this entire structure and replace this entire structure with an input impedance, and we end up with simply a voltage division solution. So let's attempt to do that. So we have a 100 ohm resistor here at the end of this transmission line of a wavelength or length of quarter wavelength in length.
It's like you got a problem with concentration.
We can go through and we can use our special case to calculate the input impedance there, 150 ohms squared divided by 100, and that would be 225 ohms. And again, as a sanity check, if this value 100 ohms is less than 150, then the input impedance needs to be greater than 150. In fact, greater than 150 in the same proportion that 100 ohms is less than 150. So 225 ohms is the input impedance, and so we can replace this entire structure in our circuit with a resistor of 225 ohms. So here's this is what we've done. Replace the remaining structure down here with its input impedance of 225 ohms. We have a voltage division problem to determine this port 1 voltage, the total voltage of port 1. It's very simple, and it turns out to be 0.9 times the open circuit source voltage VG. That voltage V1 by KVL, you notice, must be equal to the total voltage on this transmission line when evaluated here at the beginning of the line at the minus lambda over 4. So from this analysis right away, we know the total voltage at one end of our transmission line. And so we need to use that solution to propagate down and determine the voltage now at the other end of the transmission line. So we know then the total voltage at the beginning of the line here. We also could have determined I1 and determined then the total current at the beginning of the line as well. And there we'd have then two values on our transmission line, and we could use that to solve for our two unknown wave amplitudes, V0 plus and V0 minus. And once we knew that, then we could use, if we had the general solution of the total voltage, and we could use that to define or determine the port 2 total voltage simply by taking the total voltage at the end of the line where the load is at port 2. So again, we can make this into a boundary condition problem. Once we have these values, we could solve for the unknown wave amplitudes and then determine the current and voltage anywhere, and that would include, of course, the location of the line Z is equal to 0 where port 2 is located. Now, that's not a hard process to do that. It'd take a little bit of time, but it's not too difficult. And certainly we've done it several times in the past. But instead, because we have the special case of lambda over 4 in the length of the transmission line, we know we can use our periodic transmission line identities. And these are, again, very useful. If we have a quarter wavelength transmission line and I know the current on one end of the line, I can immediately determine the voltage on the other end. Or if I know the voltage on one end of the line, I can immediately determine the current on the other. I don't have to solve for boundary conditions. We don't have to determine wave amplitudes. We can immediately determine one from the other. And the identity that we'll use here is this one. If I know the voltage at one point on the transmission line, let's say the beginning of the line, I can determine the total current immediately on the other end of the line if it's a quarter wavelength further down. All right, so I know the value, total voltage at some index value. I can determine the total current at that same index plus lambda over 4. In other words, lambda over 4 further in the direction of increasing Z. All we have to do is take the total voltage, divide by Z0 of the characteristic impedance of the transmission line, and multiply it by minus J. So let's do that now. So the beginning of our transmission line here is at a location Z is equal to minus lambda over 4. So in our identity, this value Z1 is minus lambda over 4. This is the location here at the beginning of the line. And then we move a quarter wavelength further down the line in direction toward the end of the line there. And by doing so, of course, we move a quarter wavelength. And so we add a quarter wavelength to minus lambda over 4, and we get 0, which is the index here at the other end. And so the current at this end of the line, at Z is equal to 0, can be determined from the voltage at this end of the line. We simply take this value, which is 0.9 Vg, and divide by Z0 and multiply by minus J. And when we do that, this is our result. This is our current here at the other end of our transmission line. We go directly from the voltage to the current. Again, simply divided by 150 and multiply by minus J. Notice it's in terms of the generator voltage. And again, this is everything's in terms of this. This is our independent variable. So we take this current, and what we're looking for is the port 2 voltage. What is the port 2 voltage? Well, by KVL, that's simply the voltage across this 100 ohm resistor, and so we can use Ohm's law to determine that voltage. We know the current now, based on our identity. We've figured out the current. We'll multiply that by 100 ohms, and that gives us then the voltage across this load, and therefore, by KVL, that voltage is equal to port voltage V2. So immediately we've gone from port voltage V1 to port voltage V2 by using a simple identity and Ohm's law. We'll now go and find the normalized wave amplitudes so we can determine the scattering parameters. So first let's look at the normalized wave amplitude of the scattered wave at port 1. Of course, that notation is B for a scattered wave and 1P for the value, the complex value at port 1. What is the normalized wave amplitude? Well, it's simply the minus wave voltage when evaluated at that port plane, divided by the square root of the characteristic impedance of the transmission line connected to that port plane. Notice that's Z01. That's not the transmission line inside the device itself. It's the transmission line external to the device, the one that's connected directly to the port 1 plane, and that value, of course, is 25 ohms. What is the scattered wave? What is V minus? Well, we know V minus is simply the difference between the total voltage and the incident voltage. Incident plus reflected, or incident plus wave plus minus wave, is equal to the total voltage. We know the total voltage, we just determined that. It's 0.9 VG. The incident voltage on port 1 we know because we have a matched source on port 1. We have a source whose impedance is equal to 25 ohms, and therefore we know that the incident wave voltage, when evaluated at the port plane where that source is attached, the matched source is attached, is going to be equal to 0.5 VG. So we take the 0.9 we just calculated, we take the subtract from it 0.5 VG, which is the case because we have a matched source, and we do the math, and we get this result for our normalized scattered wave amplitude at port 1. We follow a similar procedure to determine the normalized wave amplitude for the scattered wave at port 2 now. So this would be B2, and same procedure as before. Carefully, we make sure we put the right value of characteristic impedance in here. It is equal to 100 ohms because that is the transmission line that is connected external to port 2. Again, it's not 150, it's 100 ohms. We determined the total voltage on the previous analysis for port 2. We know that the incident wave, yes, we have on port 2 is going to be equal to 0. We put a matched load on port 2, so there can be no incident wave. There's just a single incident wave in this analysis because we're doing our scattering parameter experiment. We only have one incident wave, and that's at port 1. So the incident wave at port 2 is 0, and we determine then the normalized scattered wave amplitude for port 2. Again, it's in terms of the open circuit source voltage VG. We said there was only one incident wave, and that was the wave incident on port 1. And so we need to determine it as well. And the normalized incident wave amplitude of port 1 is simply the plus wave voltage evaluated at the port plane. Now, I want to emphasize that plus wave voltage, that is the plus wave voltage on the 25 ohm transmission line. This is not the plus wave voltage on the 150 ohm transmission line. And then we divide that the square root of the characteristic impedance of 25 ohms. So what is the plus wave voltage on the 25 ohm line at the port 1 plane? Well, we've used this answer twice already in this analysis. We know that value is VG over 2, 0.5 VG. That's because we used a matched source, matched to 25 ohms. We know this is true. We don't need to calculate, we just write it down. Then multiply by 1 over the square root of 25, and we get 1/10 VG as that normalized wave amplitude for the wave incident on port 1. The final step for this experiment is to determine the scattering parameters. Now, we have an incident wave on port 1, and we've terminated port 2, so we can only determine the values in the first column of the scattering matrix. This is our first experiment to determine the column 1 values, specifically the values of S11, and right below it, the value of S12. The ratio of the normalized wave amplitudes for each port, both scattered and incident, and we get a value of 0.8. For S21, we take B2, the scattered wave at port 2, and again divide by the same incident wave at port 1, and we get this result. Notice the VGs cancel out. The open circuit voltage value, V sub G, cancel out here, and the answer is independent of that value, as it must be. If you get a result that is dependent on the source voltage, then you have the wrong answer. The circuit we have here is fully defined in terms of the length of the transmission line, lambda over 4, the characteristic impedance, 150 ohms, and the transmission line characteristic impedance attached to them, 25, and whatever I said, 100 ohms. So it's a fully described circuit. There's no unknowns there. We need a number as a result, and we did get a number here. And again, if VG shows up in your answer, you've done something wrong. Now we're only halfway done. We determined the first column. Of the scattering matrix. by putting a matched source on port 1 and a matched load on port 2. Now we need to flip the problem, and we need to determine the second column of our scattering matrix. We need to put a matched source on port 2 and now a matched load on port 1. So we're only halfway there. Now you might say, gee, can't we use symmetry to speed things up? We've done this before. We didn't have to find the second column because we applied some symmetry. But this structure is not symmetric. Sure, the transmission line in the middle, the quarter wavelength, it's symmetric, but what we've done is attach two transmission lines to either side, and those are unequal with respect to each other. We have 25 and 100 ohms, and so the plane of bilateral symmetry is destroyed by connecting dissimilar transmission lines. We have an unbalanced circuit in that standpoint, and so we cannot apply our symmetric arguments to try to determine the values of S22 or S12. So this is the resulting circuit now that we have to analyze for the second column in our scattering matrix. Again, we have a matched source, but remember the source impedance now is 100 ohms, not 20 or 25. And we have a matched load over here. Again, that matched load is 25 ohms, not 100. So make sure that you get this correct. Again, this is key to the transmission line characteristic impedance attached to port 2, and this is equal to the characteristic impedance of the transmission line of port 1. Now we look at this and it looks kind of weird. We've never really drawn a circuit in this way. When we had a terminated transmission line with the source attached, we always put the source on the left and the load on the right. Now, we can do the same thing here. To try to make things a little more comfortable for us, we can take simply the entire circuit and just flip it around, right? Just rewrite it. It's sort of like pretend you've run around the back side of this sheet of paper and are looking at the structure there, and now the source would be on the left. Hopefully this looks better too now. We feel more comfortable. The source is on the left and the load is on the right. Again, all we did was simply flip the circuit around, rewrote it, flipped it around the other way. We haven't changed anything at all. And that's important to notice, we haven't changed anything at all. So when we flip it, this voltage here, which was the voltage where the source is attached, remember that is port 2. So we have port 2 on the left here, and we have port 1 on the right side now. All right, so we flipped everything over, and we did that. Port 1 went to port 2, and port 2 went to port 1. But otherwise, it looks exactly the same as what we're used to. Now, we're going to define an index here, and I'm going to define the index increasing as we go to the right, as we move toward the passive load, because that's typically how we've set up that index. We're going to call this Z is equal to 0, where the load is attached, and Z is equal to minus lambda over 4, where the source is attached. From the telegrapher equations, we get a total voltage and a total current, and this is all the same as we had before. Again, the only thing weird about this now is that this voltage right here is the port 2 voltage, so we call this V2, and this current right here is the port 2 current, so we call that I2. Down here at the other end, this voltage is the port 1 voltage. Otherwise, it looks exactly the same as the circuits that we've certainly analyzed in the past. Well, we could go through and do the analysis precisely as we did for determining S11 and S21. There we used the accordion. We crushed down to equivalent circuit. We applied a voltage division. Then we applied one of our identities, periodic circuit identities, to take the voltage at one end and immediately determine the current and thus then the voltage at the other. So it was a very simple process. We really didn't have to worry anything about telegrapher equations or propagating waves. We really kind of made it more into a circuits problem once we applied the periodic identity of a quarter wave transmission line. In this case, we could do that, but in this case, let's do a more traditional way, just to show you, again, any valid method is valid, and so let's look at doing it in more classical terms with respect to telegrapher equation solutions and with respect to boundary conditions. So we know on our longer transmission line, our 150 ohm transmission line, it has to satisfy this form because it's a transmission line, has to satisfy telegrapher equations for total voltage, and then therefore likewise for the total current. In this case, each of these is written in terms of the wave amplitude V0 plus, and of course right now we have no idea what V0 plus is. All right, so let's apply our first boundary condition, and that's at the end of the line at z is equal to 0. This is where the load is located. And that boundary condition simply says that the reflection coefficient function, when evaluated at the end of the line where the load is, must be equal to the load reflection coefficient. The load reflection coefficient can be determined. It's minus 5/7, and therefore the gamma, the reflection coefficient at z is equal to 0, must be equal to minus 5/7. Well, remember, by definition, the reflection coefficient at z is equal to 0 is the value gamma 0. It shows up in our telegrapher equation solutions. And so we put these pieces together. Again, this is true by definition. The second equality is true by boundary condition. We know this is equal to that, and therefore we can say gamma 0 is equal to minus 5/7. We insert that fact into our telegrapher equation solutions, and now we have the total voltage and total current. But we still don't know what V0 plus and we don't know what V0 plus is in either case. We need to determine that. And when we do that, we'll find that it will be a function of open circuit source voltage, VG. Well, to determine V0 plus, we need to apply another boundary condition, and there's one more boundary. We already did the boundary at z is equal to 0. We need to go to the other end of the transmission line to find our second boundary at z is equal to minus lambda over 4. Let's go through and evaluate the total voltage at that end of the line, and we get this result again in terms of V0 plus. Likewise for the total current, when we evaluate, we get a result in terms of V0 plus. So now we know the voltage and the current at the end of the line where the source is attached, where that matched source is attached. So the boundary condition where we have this Thevenin source, we've looked at many times. We apply KVL around this loop. We also apply Ohm's law here, involving a KCL with this current, and we come up with this equation. This voltage VG is equal to this voltage plus the voltage drop across the 100 ohm resistor, a voltage drops that's determined by the current now flowing through it, which is this current at the beginning of the line. So this becomes our boundary condition equation. It involves both the total voltage and total current here at the end of the transmission line. Remember, these are numbers. We have to evaluate them for a specific value of minus lambda over 4. And when we do that, we get numbers. Notice no functions of z here. Our number, however, is dependent on this unknown wave amplitude, that constant V0 plus. But we have a relationship now between V0 plus and the independent variable VG. So we take that second boundary condition equation and we solve for V0 plus in terms of the independent variable VG. We now then can take that result for V0 plus and insert it into our total voltage, the solution, the telegrapher equation solution, and this now becomes our total voltage along our transmission line at any and all points in terms of the complex value, which is VG, the independent variable of the matched source. Notice this is a function of position z. What we care about now is what is the value of the total voltage at two places on the transmission line, at one end and on the other. And that would, of course, give us the port voltage V1 and V2. So let's do that now. Okay, so from KVL we know the port voltage V1. Remember, that's the one all the way down here. That port voltage V1 is simply the total voltage along the transmission line when evaluated here at the very end at z is equal to 0. So we take that total voltage solution that we had and we evaluate it at one specific point at z is equal to 0 all the way down here, and by KVL that must be equal to port voltage V1. So we evaluate that, we get this result again in terms of the independent variable VG. Likewise for V2 we evaluate the total voltage now right here at the beginning of the line at z is equal to minus lambda over 4. We insert that in there and we get this number, 0.9 times the source voltage VG. That is the port 2 voltage, all the way up here at this left side. All right, so now we can determine the wave amplitudes, the normalized wave amplitudes, and this is the same process as before. And you get the minus wave voltage. You get that from the difference between the total voltage V2 and the incident wave on port 2. And so we just calculated the total voltage V2. We subtract the total incident voltage, rather, of 1/2 VG there, and this becomes the value now of the scattered wave at port 2. Now you look at that and you say, well, this is different than what we had before for the scattered wave at port 2 in the previous half of the analysis. And that's true. And the reason that's true is because now the incident wave is on port 2 as opposed to having the incident wave on port 1 as it was before. So these answers won't be the same. So this is the, again, normalized wave amplitude for the scattered wave, B wave, at port 2. Now, B1, the normalized scattered wave amplitude, I should say, scattered wave amplitude at port 1, take the V minus at that port, which again is the difference in the total voltage and the incident voltage. The total voltage we just got through calculating. The incident voltage is 0 now on port 1 because that's terminated a match load. And then we divide by the square root of 25. Be careful here. 25 is the characteristic impedance of the transmission line connected to port 1. Again, students oftentimes will put the wrong value in here. Make sure that you put the right value in. Do a little math, and this becomes your normalized scattered wave amplitude at port 1. And finally, we determine the normalized incident wave amplitude at port 2. Again, only one incident wave, and that's at port 2. And so we determine that the V plus, the incident wave voltage, we know is simply 1/2 of the matched source voltage VG. So VG over 2 or 0.5 VG. Then we divide by the characteristic impedance of the transmission line connected to port 2. Again, be careful here. That's the square root of 100. And this becomes the normalized wave amplitude of the incident wave at port 2. Finally, then, we determine the remaining last two values of our scattering matrix, the elements of the second column in our scattering matrix. This was the second experiment that we did when we put a matched source onto port 2 to have an incident wave on port 2 and port 2 only. From the definitions of the scattering parameters, then, we take the normalized wave amplitudes, and we can determine S22 and the normalized wave amplitudes and determine S12. And that completes the scattering matrix now for this device. Again, we look at this, there are no VGs anywhere, there's no I1s or anything else in there, any variable names. This is a numeric answer because our circuit that we're analyzing for the scattering matrix is completely defined numerically. Just three characteristic impedances and a length of transmission line. All you need to describe that device, and every one of them was numerically determined, and so that's why the answers here are numeric. So the question is, are these answers correct? We could go back and check our work 3 or 4 times and think about it and all that kind of stuff. But it's helpful to perform a sanity check on the scattering matrix. And usually in everything that we do, we can apply a sanity check to our scattering matrix and see if it has some of the attributes that we would attribute to it based on the circuit that we are analyzing. So sometimes you can pass the sanity check but have the wrong answer, but usually that doesn't happen. If you make some mistake along the way, that will mess up one of the attributes that you're looking for, and you'll recognize that you have the wrong answer. I'm not as nearly as severe in grading if you give me a wrong answer that's at least plausible, that passes the sanity checks. But if you give me an answer where it's not plausible at all, it couldn't possibly be correct, and didn't recognize that that's the case, then I get more grumpy and less accommodating when it comes to grading. So always go through and look at your answers and say, hey, does this make sense? Could this actually be the right answer given the circuit that we have? So what would we look at here from this scattering matrix? How would we determine whether it passes the sanity check? There's a couple things we can look at here. First, we look to see if the scattering matrix itself is symmetric. And again, by symmetric, we're saying the matrix is. The circuit is not symmetric, but if the circuit is reciprocal, which all the circuits we look at will be, then the resulting scattering matrix must be symmetric. In other words, for a two-port device or 2 by 2 matrix, scattering parameter S21 must be equal to scattering parameter S12, and it turns out it does. Notice we didn't use this fact anywhere in the analysis. We independently determined S12 and then went through and determined S21, two different situations, two different sources and loads, yet we got the same answer there. If we didn't, we know we've done something wrong. Now, this is not a symmetry argument. Sometimes we can make the argument that S12 and S21 must also be equal because of the symmetry of the circuit. If we have a plane of bilateral symmetry, plane of bilateral symmetry, D1 symmetry, then we can make that argument. Here, there's no symmetry reason why S12 and 21 should be the same. The reason is because of reciprocity. And again, that's basically always the case when we analyze these circuits. So the device is reciprocal and the off-diagonal elements are equal to each other across that diagonal plane. It's a symmetric matrix. The first sanity check has been passed. We look at this circuit we're analyzing, get the scattering matrix for, and we recognize that it's a quarter wave length of lossless transmission line. There aren't resistors in there. It's a lossless transmission line. This is a lossless device. And because it's a lossless device, the resulting scattering matrix must be unitary. In other words, the columns of the scattering matrix must form an orthonormal set. Each column must have a magnitude of 1, and the inner product between the two must be equal to 0, the conjugate inner product or Hermitian inner product. So let's go through and see if that's the case. If we look and see the magnitude of the first column, we simply take the magnitude squared of S11 plus the magnitude squared of S21, and we add them both together and we get 1, a magnitude of 1. So this is a normal vector for column 1, as it should be. For the second column, S12 magnitude squared plus S22 magnitude squared, it turns out to be likewise a value of 1. So far, so good. The last step is often the hardest for students to do, and that is to determine whether the column vectors are orthogonal to each other. And so to do that, we take the first element of, in this case, the first element of the first column vector, S11, and we multiply by the first element of the second column vector. But before we do that, we take the complex conjugate of that second column vector. Basically, we're going to take the first column vector, and multiply by the complex conjugate of the second one there. The next term is to take S21, the second element of the first column, and multiply it by the complex conjugate of the second term of the second column. Multiply those two things together and we get two complex numbers, one here and one here, yet when we add them together we get a value which is equal to 0. And that says that those two vectors are orthogonal to each other. The two vectors of the scattering matrix form an orthonormal set. Each one has a magnitude of 1, and the two vectors are mutually orthogonal to each other. So the scattering matrix is unitary, as it must be since the transmission line is a lossless device. Again, if we made some mistake somewhere, almost certainly our scattering matrix would not have turned out to be unitary, and that would have told us that we made a mistake somewhere along the line. The fact that it is unitary tells us almost certainly that we have the right answer. Now, sometimes we could make a mistake that preserved the unitary nature, but it'd be very difficult for that to occur. So that's a nice thing about these analyses is you can tell when you're done whether you've done it correctly or not.
That's a good idea.
That's all, folks.